Now we are in the parametric settings where x and y are given as functions of some parameter t. And usually we think of t as time. So y is not a function of x. It's not given as a function of x. Both of the coordinates x and y are given as functions of t, independent parameter or variable. And we're supposed to prove all these formulas we need in this course, being in parametric circumstances, settings. For the first one, for the slope, there is almost nothing to prove. So slope by the definition is the first derivative of function y with respect to x. But again, y is not given as a function of x. And the easiest trick possible, similar to what we did in polar system of coordinates already, we just introduce t. We divide numerator and denominator by the same quantity, dt. And that is how we will get the derivative of y with respect to t in the numerator and x prime, derivative of x with respect to t in the denominator. So to calculate slope in parametric settings, just calculate two derivatives, y with respect to t and x with respect to t, and calculate the ratio of those. We're done with the slope in parametric system. Okay, now let's consider speed of a particle. As it was mentioned, we think of t almost always as time in most of the cases. So, and we may think of a particle that is moving in 2D space in this case somehow, and we need to calculate speed of this particle. Okay, let's consider what we can do here, and let's move down this red hill. So let's imagine that's the curve, that's the path that the particle gonna move, slide down. So let's say from point A to another point B, and we can imagine x and y axis. We are in parametric settings, but we always can imagine x and y axis. Okay, and then while moving from initial point to the destination, this point will be sliding down the red hill, and x and y will be changing. Y will be changed in such a way that change of y coordinate is equal to delta y, and x will be changed as well. The change of x is delta x. What else? We need also this, let's say, blue hypotenuse of the right triangle. So the question is how to find the delta s, the distance for now, the distance of this particular small piece of the curve, the distance. It is easy. We go delta s is equal to, we go red is equal to blue first of all. That's the regular approximation, regular calculus approach. We imagine delta x and delta y infinitely small. Therefore, the red piece of the curve eventually will be equal to the blue hypotenuse. And that's handy. So if the red is equal to blue, then we can use Pythagorean theorem to calculate delta s. And it's equal to sum of the squares of the legs and square root out of this combination. Okay, so this is delta s. But we need actually speed of the particle. This is the distance that the particle will cover in some period of time. And we're going to imagine this and introduce this period of time as a small interval dt. Then we're going to divide left side of the equation. Then we have to divide the right side of the equation by the same quantity as well. Okay, and from here we can recognize the final outcome, the final result. What's the delta S or ds over dt, infinitely small interval of time? This is instantaneous speed of the particle. And what do we have on the right? We can recognize on the right sides of those equations, we have identical expressions. So if we introduce dt under the square root, it will appear with the square. So that's the same, delta y squared divided by delta or dt squared. That's what we have here. And that's what we have here actually. And delta x squared divided by dt squared, it will be squared after introducing inside under the square root. So we're going to have dx over dt squared. So those guys are derivatives of the given functions, x as a function of t and y as a function of t. We can calculate derivatives, square them, calculate square root, and we're done. That's the speed. That's the way to calculate speed of a particle in parametric settings system. Okay, let's do one more. Let's do arc length, because we're going to do it really fast, really fast. So arc length. So let's think about the same small arc length for now. So how to calculate distance? Okay, since we already have the speed of the particle, so we just need to multiply this speed times period of time, interval of time, dt, and that will give us the distance of this small piece of the red curve. Then we need to add up all these pieces of the curve. And the way we do it in calculus 2 is integration. And we're done. So this is the formula to calculate arc length in the given interval of the parameter of time from t is equal to a to t is equal to b. Okay, so we have proved 3 formulas out of those 4. Let's consider the last one, a little bit more complicated, in the next presentation.